In a corner-grounded distribution system, one phase, typically phase A, is grounded at the panel board or distribution transformer. This configuration creates a 3-wire, single-phase system. This system includes one grounded conductor and 2 hot conductors, phase B and phase C. Regarding panel board selection, in a corner-grounded system, 2 primary options exist. Firstly, one can utilize 3-phase panel boards equipped with a neutral bus. This setup provides a dedicated neutral bar to which the grounded conductor, phase A, is connected. When using this configuration, 3-pole circuit breakers should be employed for all loads. Secondly, an alternative is to use single-phase panel boards that also have a neutral bar. With this approach, the grounded conductor, phase A, is connected to a neutral bar within the panel board. 2-pole circuit breakers are used for single-phase loads, while 3-pole circuit breakers are used for 3-phase loads. Concerning circuit protection, it is critical to ensure that the grounded conductor, phase A, is never opened by a circuit protection device, as explicitly stated in the National Electrical Code, section 240.20. 3-pole circuit breakers must be used for 3-phase loads, irrespective of the panel board type selected. 2-pole circuit breakers are suitable for single-phase loads, but only when installed in single-phase panel boards. Proper identification of conductors is crucial. The grounded conductor, phase A, must be clearly identified according to National Electrical Code sections 200.6 and 200.7. This identification can be achieved by using white insulation or by painting the bus bar or wire white. The other 2 phases, B and C, must be identified with contrasting colors, commonly black and red. Other considerations for corner-grounded systems include their typical use in industrial settings where low fault currents are prevalent. The grounded conductor may carry substantial current, especially during fault conditions. Therefore, ground fault protection devices, GFCIs, are highly recommended for personnel protection. It is always advisable to consult with a qualified electrician. Strict adherence to all applicable codes and regulations is necessary when designing and installing a corner-grounded distribution system. The importance of using appropriate circuit breakers is paramount for ensuring safety and compliance within electrical systems. In corner-grounded systems, the choice between 2-pole and 3-pole breakers hinges on the type of load being served. For single-phase loads and single-phase panel boards, 2-pole circuit breakers are typically used. These breakers are designed to protect a single-phase circuit, interrupting the current flow in both the hot and neutral conductors in case of an overcurrent or short circuit. However, for 3-phase loads, regardless of the panel board type, 3-pole circuit breakers are mandatory. These breakers provide simultaneous protection for all 3 phases of the circuit. Using a 2-pole breaker on a 3-phase load would leave one phase unprotected, posing a significant safety hazard. The requirement to protect all phases stems from the nature of 3-phase power. Each phase carries a portion of the total load, and a fault on any one phase can lead to imbalances and potential damage to equipment. 3-pole breakers are designed to detect overcurrent or short-circuit conditions on any of the 3 phases and to interrupt the current flow on all 3 simultaneously, preventing damage and ensuring safety. Furthermore, the National Electrical Code mandates the use of 3-pole breakers for 3-phase loads to prevent single-phasing. Single-phasing occurs when one of the phases in a 3-phase system is lost, either due to a blown fuse, a trip breaker, or a break in the conductor. When a 3-phase motor operates in a single-phasing condition, it can draw excessive current in the remaining phases, leading to overheating and potential motor failure. 3-pole breakers mitigate this risk by tripping all 3 phases simultaneously, preventing the motor from continuing to run in a single-phasing condition. The selection and installation of circuit breakers must always comply with the National Electrical Code and any local electrical code. These codes specify the types of breakers that are permitted for various applications, as well as the required ampacity and interrupting rating of the breakers. It is crucial to choose breakers that are properly rated for the load they are protecting and that are approved for use in the specific equipment in which they are installed. Incorrectly sized or improperly installed breakers can lead to nuisance tripping, which can disrupt operations, or more seriously, it can fail to protect the equipment and personnel from electrical hazards. Regular inspection and testing of circuit breakers are also essential to ensure their continued proper functioning. Breakers can degrade over time due to factors such as corrosion, vibration, and exposure to high temperatures. Regular testing can identify breakers that are no longer functioning correctly and that need to be replaced. Maintaining a comprehensive record of all circuit breakers, including their type, rating, location, and maintenance history, is a best practice for ensuring the safety and reliability of electrical systems. The use of ground fault circuit interrupters, GFCIs, and arc fault circuit interrupters of size further enhances the safety of electrical systems. GFCIs are designed to protect against electrical shock by detecting small imbalances in the current flow between the hot and neutral conductors. If an imbalance is detected, indicating that current is leaking to ground, the GFCI will trip the circuit, cutting off the power and preventing a potentially fatal shock. GFCIs are designed to protect against fires caused by arc faults. Arc faults occur when electricity jumps between conductors, creating a high-temperature arc that can ignite nearby materials. GFCIs detect the unique characteristics of arc faults and trip the circuit, preventing a fire from starting. The NEC requires the use of GFCIs in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electrical shock. The NEC also requires the use of GFCIs in many locations, such as bedrooms and living rooms, where there is a higher risk of arc faults. Using both GFCIs and GFCIs provides a comprehensive approach to electrical safety, protecting against both shock and fire hazards. Understanding the specific requirements of the NEC and local electrical codes is crucial for ensuring the safety and compliance of electrical systems. These codes are constantly evolving to reflect new technologies and best practices, and it is important to stay up to date on the latest requirements. Consulting with a qualified electrician is always recommended when designing, installing, or modifying electrical systems. A qualified electrician has the knowledge and experience to ensure that the work is done safely and in compliance with all applicable codes. Furthermore, regular electrical inspections can help to identify potential hazards and ensure that the electrical system is functioning properly. Inspections should be performed by a qualified electrical inspector who is familiar with the NEC and local electrical codes. By following these best practices, it is possible to create and maintain electrical systems that are both safe and reliable. The principles discussed here apply broadly to electrical systems, including corner-grounded systems. Corner-grounded delta systems introduce unique grounding considerations that necessitate a thorough understanding of their characteristics. In a corner-grounded delta system, one of the phase conductors, typically phase A, is intentionally connected to ground at the source, usually the transformer. This connection establishes a reference point for the system voltage and provides a path for fault current to flow back to the source. Unlike other grounding configurations, such as solidly grounded or impedance-grounded systems, the corner-grounded delta system does not have a neutral conductor. The absence of a neutral conductor has several implications for the design and operation of the system. Firstly, the voltage to ground on the ungrounded phases is equal to the phase-to-phase voltage. For example, in a 240-volt corner-grounded delta system, the voltage to ground on phases B and C would be 240 volts. This higher voltage to ground can increase the risk of electrical shock if proper precautions are not taken. Secondly, the fault current in a corner-grounded delta system can be relatively high. When a ground fault occurs on one of the ungrounded phases, the fault current flows through the grounding conductor back to the source. The magnitude of the fault current is limited only by the impedance of the grounding conductor and the source impedance. This high fault current can cause significant damage to equipment and can pose a serious safety hazard. Thirdly, the detection of ground faults in a corner-grounded delta system can be more challenging than in other types of systems. Because there is no neutral conductor, traditional ground fault relays that monitor the current in the neutral conductor cannot be used. Instead, ground fault detection in a corner-grounded delta system typically relies on residual current relays or zero-sequence current transformers. These devices monitor the sum of the currents in the three-phase conductors and detect any imbalance that indicates a ground fault. Despite these challenges, corner-grounded delta systems offer several advantages in certain applications. One advantage is their simplicity and lower cost compared to other grounding configurations. Because there is no neutral conductor, the system requires fewer components and is easier to install. Another advantage is their inherent immunity to single-point grounding faults. In a solidly grounded system, a single ground fault can cause a widespread outage. However, in a corner-grounded delta system, a single ground fault will not necessarily cause an outage. The system can continue to operate with the ground fault present, although it is important to locate and clear the fault as soon as possible to prevent further damage. Corner-grounded delta systems are commonly used in industrial applications where reliability is critical and where the risk of electrical shock is carefully managed. Examples of such applications include metalworking shops, welding facilities, and other heavy industrial environments. When designing and installing a corner-grounded delta system, it is important to follow all applicable codes and standards, including the National Electrical Code and any local electrical codes. These codes specify the requirements for grounding, bonding, overcurrent protection, and other safety measures. It is also important to use qualified personnel who are familiar with the unique characteristics of corner-grounded delta systems. Proper grounding and bonding are essential for ensuring the safety and reliability of corner-grounded delta systems. Grounding refers to the intentional connection of a conductor to earth, while bonding refers to the connection of conductive parts to each other to create an electrically continuous path. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, while the purpose of bonding is to minimize voltage differences between conductive parts. In a corner-grounded delta system, the grounding conductor is connected to the grounded phase conductor at the source. This connection provides a reference point for the system voltage and ensures that the voltage to ground and the ungrounded phases is limited to the phase-to-phase voltage. The grounding conductor must be sized according to the requirements of the National Electrical Code, which specifies the minimum size of the grounding conductor based on the size of the phase conductors. Bonding is equally important for ensuring the safety of corner-grounded delta systems. All conductive parts that are likely to become energized, such as equipment enclosures, metal conduit, and structural steel, must be bonded together to create an electrically continuous path. This bonding helps to minimize voltage differences between these parts and reduces the risk of electrical shock. The bonding conductors must also be sized according to the requirements of the National Electrical Code. Overcurrent protection is another critical aspect of corner-grounded delta systems. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect the system from overloads and short circuits. These devices must be properly sized and coordinated to ensure that they will trip quickly and reliably in the event of an overcurrent. In a corner-grounded delta system, the overcurrent protection devices must be selected based on the specific characteristics of the system, including the fault current level and the impedance of the grounding conductor. The National Electrical Code provides detailed requirements for the selection and coordination of overcurrent protection devices. Regular maintenance and testing are essential for ensuring the continued safety and reliability of corner-grounded delta systems. Maintenance activities should include visual inspections of the grounding and bonding connections, as well as testing of the overcurrent protection devices. Testing should be performed according to the manufacturer's recommendations and the requirements of the National Electrical Code. Any deficiencies that are identified during maintenance or testing should be promptly corrected. By following these best practices, it is possible to design, install, and maintain corner-grounded delta systems that are both safe and reliable. These systems have been used for many years in industrial applications, and when properly implemented, they can provide a cost-effective and reliable source of power. The evolution of electrical standards and practices continuously shapes the implementation of corner-grounded systems, highlighting the need for ongoing education and adaptation. Modern safety protocols emphasize proactive measures such as regular inspections, advanced monitoring technologies, and comprehensive training programs for personnel involved in the operation and maintenance of these systems. The integration of digital technologies allows for real-time monitoring of system parameters, enabling early detection of potential faults and facilitating timely intervention. These advancements contribute to enhanced safety and operational efficiency, reducing the risk of electrical hazards and minimizing downtime. In addition to technological advancements, evolving codes and standards play a crucial role in shaping the design and implementation of corner-grounded systems. Regulatory bodies continuously update electrical codes to incorporate new safety requirements and best practices, reflecting the latest research and industry experience. Compliance with these codes is essential for ensuring the safety of personnel and the reliability of equipment. Therefore, staying abreast of the latest code revisions and incorporating them into system design and maintenance practices is paramount. The use of advanced materials and components also contributes to the improved performance and safety of corner-grounded systems. Modern insulating materials offer superior dielectric strength and resistance to environmental factors, reducing the risk of insulation failure and electrical breakdown. Similarly, advanced circuit breakers and fuses provide faster and more reliable overcurrent protection, minimizing the potential for damage to equipment and personnel. The selection of appropriate materials and components is a critical aspect of system design, requiring careful consideration of the operating environment and the specific requirements of the application. Furthermore, the increasing emphasis on sustainability and energy efficiency has influenced the development of corner-grounded systems. Modern designs incorporate energy-efficient transformers and other components to minimize energy losses and reduce the overall carbon footprint of the system. The use of renewable energy sources, such as solar and wind power, is also becoming increasingly common in conjunction with corner-grounded systems, further enhancing their sustainability. In conclusion, the safe and efficient implementation of corner-grounded systems requires a holistic approach that encompasses ongoing education, adherence to evolving codes and standards, the use of advanced materials and components, and a commitment to sustainability. By embracing these principles, it is possible to harness the benefits of corner-grounded systems while minimizing the associated risks.